Hello, let's start with a simple question. In this design, the TX already has FFE. The TX FFE is digital. It works on bits. It uses the shift register that are already inside the serializer. So it's natural to ask, why can the RX do the same thing? Why does the RX need sample and hold amplifier? Why can't we just use digital flops? The answer is very simple. On the RX side, before the slicer, we do not have bits yet. We only have analog waveform. The slicer has not made a decision yet, so the RX FFE must work before the signal becomes digital. That means the RX FFE must work in the analog domain. This is the key difference. TX FFE works after the data is already digital. RX FFE works before the data is decided. So the real question is not why not copy the TX FFE? The real question is, how do we build an FFE for an analog signal running at 56 gigabaud? Let's first look at why the TX FFE is cheap. The TX has a serializer. The serializer takes parallel data and sends it out as high-speed serial data. Inside the serializer, there's already a chain of registers. These registers hold the current symbol, the previous symbol, and the older symbols. They are already spaced by exactly 1 UI. So for TX FFE, delay line is already there. We just tap different register stage. Then we multiply each tab by a coefficient. Then we add them together and send the result to the DAC. This is why TX FFE is almost free. It uses digital data. It uses existing registers. It does not need a new analog delay line. It does not need a new sampler. It does not need a very high-speed analog buffer. But now, let's look at the RX side. At the RX input, the signal is not digital yet. It's still a fast analog waveform. There's no shift register holding analog samples. There are no clean bits yet. There's only voltage moving on wires. So the RX cannot simply tap existing digital flops. Those flops do not exist before the slicer. This is the main point. TX FFE tap an existing digital delay chain. RX FFE must create or use analog samples. That is a much harder problem. So think about the analog delay line image for 5 seconds. Bingo! You can delay the signal by 1 UI. Then you can delay again by another UI. Then you apply tap weights and add the signal together. At 56 gigabaud, 1 UI is only about 17.8 picosecond. That is extremely short. To make a delay with transmission line, the line would take a lot of area on chip. For 3-tap FFE, we need 2 delay sections. That means the layout becomes large. Also, the line has loss. So the signal becomes weaker before we even try to equalize it. Another way to use buffer delay cells. A buffer has some delay, so we can put several buffers in series. But this also has problems. The delay of buffer changes with the process, voltage, and temperature. So the delay may not stay at exactly 1 UI. We may need tuning circuits. We may need calibration. We need extra control logic. All of this adds power and area. Even worse, the delay cells can hurt the signal. They can add noise. They can limit the bandwidth. They can add distortion. This is not what we want. The equalizer should clean the signal. It should not damage the signal first. So a delicate analog delay line is possible, but it is expensive, hard to control, and not very clean. Then think about sample and hold amplifier image for 5 seconds. Yes, The RX already uses a time interleaved structure. For 56 gigabaud PAM4, one UI is about 17.8 picoseconds. In a quarter array RX, 4 sampling phases are used. These phases sample the input at different time points. The important point is this: the samples are already spaced by one UI, so the RX already has the time point that FFE needs. The main tab uses the current sample. The previous cursor used the sample one UI before. The post cursor used the sample one UI later. These samples are already captured by the sample and hold amplifiers, so we do not need to build a new delay line. We do not need to create a new analog memory. We simply reuse the samples that already exist in the RX data path. This is a smart idea. The sample and hold amplifier are already needed for the quadruple array RX. We are already needed for the CDR and slicer. The FFE just takes those hot samples, apply weights, and add them in the summer. So the FFE is not a big extra block. It's built into an existing sampling architecture. This saves power. It saves area. You also avoid a difficult analog delay line. Then, how about the timing accuracy? Great. The timing of the sample and hold FFE is very accurate. In a normal analog delay line, the delay depends on physical circuits. It depends on wire length. It depends on buffer delay. It changes with the process voltage and temperature. So, the one UI delay may move around, but in the sample and hold FFE, the tap spacing comes from the clock data recovery clock phases. The CDR is already locked to the incoming data. That means the sampling phases are already aligned to the data stream. So the FFE tap timing is not set by a random buffer delay. It's set by the locked clock phase. This is very powerful. If the temperature change, the CDR checked it. If the supply change, the CDR correct. If the process corner change, the CDR still locked to the input data. So the FFE tap timing is naturally controlled by the CDR. This means we do not need extra calibration. Just set the FFE tap spacing. The timing accuracy comes for free from the clock data recovery group. Now, someone may ask me a good question. Why not just use more TX FFE tabs? Why not push more equation to the transmitter and remove the RX FFE? Correct. There are 3 problems with that idea. First, the TX cannot see everything that happens inside the RX. The RX front end, such as the CTOE and VGA, can also create phase shift and ISI. The TX is far away. It cannot correct distortion that is created after the signal enters the RX. Second, stronger TX FFE causes swing. Now, when we add more TX emphasis, we take energy away from the main cursor. For PAM4, this is the PAM4. PAM4 already has a smaller eye, opening than NRZ. Each eye only gets part of the total voltage swing. So if the TX FFE becomes too strong, the main eye may become smaller. That hurts the slicer margin. Third, TX FFE is based on guess of the channel. It is the pre-distorted method. It assumes that the channel looks like, but the real channel may be different. The ball may be different. The connector may be different. The temperature may be changed. The ball package may change. RX FFE sees the actual receiver signal. It adapts after channel, after the CTOE, and after the VGA. So RX FFE corrects the real combined response seen by the receiver. That is why RX FFE is still useful. even when TX FFE already exists. Here are the summarized images showing you why we need additional RX FFE, not just TX FFE. You may know that TX FFE is cheap because the TX already has a digital delay. The CSR already holds past and current symbols in registers, so TX FFE just tap those registers and add weight bits. But RX FFE cannot copy this. Before the slicer, the RX signal is still analog. There are no digital bits yet. There are no digital flaps to tap. A normal analog delay line would be hard. You need very accurate one UI delays. You add power, you add area, you add noise and distortion. The sample and hold method solves this in a much cleaner way. The quadruple RX already has several sampling phases. Those phases already capture the input signal at one UI spacing. So the FFE can use those samples as it pre-main and post taps. The tap weights are then added in the existing summer. No dedicated delay line is needed. No extra timing calibration is needed. The CDR already controls its sample timing. This is the beauty of the design. The circuit does not add big new blocks. It reuses a structure that must already be there. That is why the RX FFE uses simple and whole amplifiers. It's not just a different way to build FFE. It's the right way for the quadruple analog receiver architecture. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video with the people who may be benefit from it.